Alpha Houston on space to ground 1 for Don. We're ready for your downlink.
Okay, I'm going to hit play.
I'm Don Pettit. I was fortunate enough to be science officer on Expedition 6 to the International Space Station. And during this expedition, we had several kinds of science that we did. We did programmatic science, which is well-planned and well-thought-out science, comes up from the ground and is orchestrated from the ground. And then we have science of opportunity. And this is science that is done at the discretion of the scientists on board space station. And this is kind of the discovery science. And during our mission, we called our science of opportunity Saturday morning science. Now we're going to look at using a water film for convection. We just saw what happens with diffusion, where you intentionally keep the film quiescent, where you don't want to have any extraordinary fluid motion. Now we're going to intentionally stir one of these films and look at the onset of fluid motion. And instead of using food coloring, we're going to use tracer particles. These are small flakes of mica. They're 5-micron diameter flakes, and it's a standard fluid tracer particle. And we're going to put a few drops of these in one of the films. We're going to stir it around and see what happens.
These films are so thin, you can disregard the flow within the thickness of the film, and so you can now investigate two-dimensional fluid flow problems.
And here we put the Teflon cannula through the film, and we give it a little stir. And now look at the resultant motion that goes on here. And this motion will take about a half hour, 40 minutes before it stops. It'll just sit there and rotate and rotate and rotate. And you've basically eliminated motion perpendicular to the film, and it just sits there and happily rotates for many, many tens of minutes. And here's a cut that goes to some time later. It's about 10 minutes later, and there'll be another cut. And it shows that as time goes on, the velocity at which this rotates slows down, and it develops more of these tracer particles laying down this spiral pattern. Here we have a time-lapse sequence showing the motion of these particles where a 10-second period is about equal to 1 orbit. And if you looked at this with your eyeball, you'd say all motion has stopped. But when you time-lapse this over a period of hours, you can see that there's still residual motion going on in this film. And you can see that this pattern continues to move in this time-lapse sequence. And this is an example of what the residual acceleration forces in a microgravity environment can do to your fluid system. It can still incite motion, and it generally rotates counterclockwise from this perspective, but every so often it stops its rotation and starts to rotate clockwise, and then it'll stop and start to rotate counterclockwise again. And this is due to the residual acceleration forces in a microgravity environment after the gross fluid dynamic forces from stirring have dampened down. And this is an example of what forces, the residual acceleration forces in a microgravity environment can do after the gross fluid dynamic forces from stirring have dampened down.
And Houston Alpha, that's it for our Saturday morning science.